In the previous lecture we started discussions on the elimination methods, and let us continue with that. So, let us take up an example. So, we have these three equations with three unknowns, and we want to solve for x1, x2, x3 by an elimination technique, which we will formally describe as the Gaussian elimination method. To see how the method works, first we will go through this example and then try to formalize this through a more general algorithm. So, the first and foremost objective is to operate on the coefficients in the coefficient matrix. So, if you write the coefficient matrix, you have 10 1 1 1 10 1 1 1 10, and if you write the augmented matrix, you have additional terms. Now, as we discussed in the previous lecture, our objective will be to convert this coefficient matrix into an upper triangular matrix. So, we want to have non-zero terms only within this portion, but not below that. So, all the terms below that should be eliminated and converted to 0. So, first we will convert the terms in the first column below the diagonal to 0. To do that, we will take the first row as the key row, using which we will eliminate these ones to make them zeros, and that key row we call as the pivotal row. So, in step 1, you have row 1 as the pivotal row. So, you want to eliminate this x1 from equation 2 using equation 1. Equation 1 conforms to row 1. So, what we will do? We will have equation 2, new equation 2 is nothing but old equation 2 minus 1 by 10 into equation 1. Okay. So, what will that imply? Your x1 will be eliminated, because this is 1 minus 10 into 1 by 10, that is 1 minus 1, that will be 0. Next will be 10 minus 1 by 10, that is 0.1. x2, x3 is 1 minus 0.1, x3 is equal to 12 minus 1.2. So, you have 9.9 x2 plus 0.9 x3 is equal to 10.8. Similarly, equation 3 is equation 3 minus again 1 by 10 equation 1, so that the first column is eliminated. So, then we have 1 minus 0.1 x2 plus 10 minus 0.1 x3 is equal to 10.8. That means 0.9 x2 plus 9.9 x3 is equal to 10.8. So, what is the corresponding matrix form? This is the original matrix form. Then after step 1, first row remains unchanged, second row now this has become 0, coefficient of x2 is 9.9, coefficient of x3 is 0.9, right hand side is 10.8. Equation 3, coefficient of x1 is 0, coefficient of x2 is 0.9, coefficient of x3 is 9.9 and right hand side is 10.8. So, this is after step 1. Then step 2, now what we will do? We will consider the second row as the pivotal row and try to eliminate the term which is in the column conforming to the diagonal element of the pivotal row. So, as we eliminated the first column, now we will eliminate the second column below the diagonal. Okay. So, to do that, now remember, now equation 2 and equation 3 have changed. So, this is new equation 2, this is new equation 3. So, these we will call as, refer to as equation 2 and equation 3, no more the original equation 2 and equation 3. So, step 2, what will be equation 3? Equation 3 will be equation 3 minus, so this has to be made 0.9. So, this, how do you make it 0.9? Just use these coefficients until, so 0.9 by 9.9 into 9.9, right. So, that makes, that converts this 9.9 to 0.9. So, this you want to apply. So, remember, so what you are doing, when we generalize we keep this in mind, the coefficient divided by the pivotal coefficient, that is the diagonal coefficient of the pivotal row multiplied by the corresponding term in the pivotal row, that is what we are doing. So, this into, in general it is equation 2. So, 9.9 was for the first term, 0.9 will be for the second term. So, for the first term we wanted to make it 0. So, that is why 9.9, for the second term it will not be 9.9 but 0.9, the second term therefore will be non-zero. So, this will be what? The first term will be 0 because this is as good as 0.9 by 9.9 into 0.9 into 9.9, that we have seen, that is the first term. Second term will be what? 9.9 minus 0.9 by 9.9 into 0.9, that x3 is equal to 10.8 minus 0.9 by 9.9 into 10.8. So, if you work it out, it may be 9.818, x 3 is equal to 9.818. So, x 3 is equal to 1, but before that let us formalize what happens after step 2. So, we have the first row 10, 1, 1, 12, second row 0, 9.9, 0.9, 10.8, third row has now changed. So, it has become 0, 0, 9.818, this one also 9.818. So, the entire system has been reduced to an upper triangular system. It required 2 steps for 3 equations. So, in general if there are n equations, it will require n minus 1 number of steps to reduce it to an upper triangular form. So, this up to this we call as forward elimination. Next will be backward substitution. So, these steps 1 and 2 we can say that these belong to forward elimination. And next will be backward substitution. So, for backward substitution we have x 3 is equal to 9.818 by 9.818, that is 1. This is from new E 3. Then from new E 2 you have 9.9 x 2 is equal to 10.8 minus 0.9 x 3. So, that is equal to 9.9 because x 3 is 1, that means x 2 equal to 1. And from new E 1 which is same as the old E 1 of course, you have 10 x 1 is equal to 12 minus x 2 minus x 3, that means x 1 is 1 because both x 2 and x 3 are 1. So, this is an example just to illustrate how the Gaussian elimination method it works. We will later on see whether it will work for all cases or not. See, whenever we are learning a method, what we are essentially following is like this. First we are trying to get a feel of the method, then we are going to see whether the method will work or not, and of course if it works, how efficiently it works. So these are the three questions that we would always like to answer. What is the method? Will it work for all cases? If it works, how efficient it is? These are the three standard questions that we will like to implicitly answer as we progress through the different methods that we learn. Now before answering the later two questions, the first question remains to be answered, that is, what is the method? We have seen what is the method through an example, but this is not general. We have to generalize this example for say n number of equations with n number of unknowns. So let us try to do that. So generalization of Gaussian elimination. To generalize the Gaussian elimination, let us consider a system of equations like this: a11 x1 plus a12 x2 in this way plus a1n xn is equal to b1, a21 x1 plus a22 x2 plus a2n xn is equal to b2. In this way, an1 x1 plus an2 x2 plus ann xn is equal to bn. We give these equations some numbers. This is E1, this is E2 in this way, this is En. So what we first make? We first make the first row as the pivotal row. So row 1 pivotal row. Then using row 1 as the pivotal row, we will eliminate all the terms which are there in the column of the diagonal element corresponding to row 1 below the diagonal. The effort is to slowly go through steps by virtue of which it will have all zeros below the diagonal. So first zeros in the first column below the diagonal. Next step will give you zeros below the second column of the diagonal. Third step will give you zeros below the third column of the diagonal in this way. So zeros before the first column of the diagonal, how you can do that? You have equation 2 will be equation 2 minus, see the first row. So how it can be eliminated? By a21 by a11 into a11 will make it a21. So that minus a21 will be 0. So E2 minus this into E1. So you can see that this manipulation is done with an objective that the corresponding terms becomes 0. So you can figure it out by putting a21 in place of this one, so that it is a21 by a11 into a11 will make this also a21, the difference will be 0. So what will be E3? E3 minus, in place of 2 it will be 3. So a31 by a11 into E1 . So in this way, what is, say Ej or Ei, whatever name you give, Ei will be Ei minus AI1 by A11 into E1. So, how do you generalize it? In place of Ei, what you are basically doing when you are considering equation number I, there you are playing with the ith row and jth column where j varies from 1 to n plus 1. You also have an extra column to accommodate the right hand side. Remember that you are writing the corresponding equation form of the augmented matrix or augmented matrix including the right hand side of the equation form. So, in place of Ei, if you write it as Ai, then subscript j. So, Ai is the first subscript for the row for ith row, ith equation and the jth column, that will be Aij minus this is Ai1. So, we keep it Ai1 divided by A11 into what is E1? E1 is A1j. If Ei is Aij, then E1 is A1j, right. The first subscript is for the row. For the ith row, if the first subscript is I, for the first row, the first equation, the first subscript is 1. Okay. So, this you are doing for step 1. Then for step 2, what will be this formula for Aij? Now let us see. It will be Aij minus, in place of Ai1 it will be Ai2, because now second row will be the pivotal row. So, this 1 indicates the corresponding number of the pivotal row. So, this will become Ai2 divided by A22 into A2j. So, in general for step number k, so generalize for step number k. What does this k indicate? It indicates what is the pivot. So, k equal to 1 means that the first row is the pivotal row, k equal to 2 means second row is the pivotal row, k equal to 3 is the third row pivotal row, and so on. So, Aij will become Aij minus Aik by Akk into Akj. So, this is essentially the formula that we are applying for the forward elimination method, and because there are 3 indices I, j and k, we can put this entire algorithm in 3 for loops. So, let us try to put that. So, first, so what we are trying to do is we are trying to now formalize the forward elimination. So, let us write the for loops for k equal to what will be the range of k? The first value of k is 1, and what is the last value of k? N minus 1. N minus 1 1th one is the last pivot, because using that the term immediately below that is eliminated. If you consider n as a hypothetical pivot, there is nothing below that, so n is not a pivot. Then for what is j, what columns you are eliminating? You are eliminating the columns. So let us look into the first case. When this is the diagonal, you are eliminating the columns below, of course the rows below, but for the columns from the right of the diagonal. So if it is A11, the next that you are looking for, so if j is equal to 1, you are looking for j equal to 2 onwards for elimination. So you are not doing it for 1, why? You are actually doing but not putting in the algorithm, because you know it will come out to be 0. So why do you waste a calculation in coming up with this equal to 0, because already you have designed the calculation so that this should come to be 0. Once you have designed this calculation that this should be come to 0, you do not repeat it once more for implementation. So for implementation you only calculate the non-zero elements. The zeros are already known that they will be zeros by virtue of this algorithm that you have implemented. So if this is k, j becomes k plus 1 to n plus 1. And what is I? K plus 1 to n plus 1, because what this is the kth row, example k is equal to 1. So you are manipulating with the rows below the, starting from just below the kth row. So k plus 1 to not n plus 1, n, there is no n plus 1 row. Now let us see, we have not yet formalized. See, I am trying to go through the mental exercise instead of writing the algorithm as it is. Let us try to go through some mental exercises to see that what should be the best way to put it. So I have just put the structure. J is from k plus 1 to n plus 1, because the you have the right hand side also included in the column, but I is up to n. Now next is it legitimate to put the for loop on j first or for loop on I first? Which one we should do? Let us try to see. See what calculation we will be doing, it depends on that. See, these are certain things, try to carefully learn. Our objective is not to just write a algorithm for Gaussian elimination. In any book you can see the algorithm and you can implement. The objective is to have a mental exercise to learn yourself how to design a new algorithm if you know the method that what needs to be implemented. So how to translate a method into a systematic algorithm, that is what we are trying to learn through this example. So now let us see, you have this aik by akk. So what you have to do is for each, so now you have ij, so immediately next step you are prompted to write aij minus aij into aik by akk. So if you have aik by akk, you can put it inside this loop, but you can also put it outside this loop by making this as I and making this as j. So let us make a conversion of that. So let us make this j, make the first one as I, because of course n plus 1 and n, those things will change. because once you enter the loop you require aik by akk. So if that is already ready before entering the loop you can just use that value. So let us say that you have r equal to ai, the ratio equal to aik by akk, because k is already known and I is already known, this is already specified. So this you can specify in terms of 2 indices. So once you know this r, you do not have to calculate it again and again and again. Once you enter the j loop, for each j now you can calculate aij is equal to aij minus r into akj. If you had put this r inside this j, what would have happened? That it would have been useless. I mean it would have not been a wrong thing, but what it would have been there is every time for a new j this will be calculated unnecessarily. This requires only the index I and k for its calculation. So when j goes from k plus 1 to n plus 1, if this r was inside, it would have gone up to that many number of times extra calculation of r unnecessarily. So this is an important thing that you have to be careful about, that what calculation you put inside a loop, what calculation you put outside the loop. You should not put a calculation inside a loop where it is not necessary to go through that many number of times inside the loop. So you put it outside the loop, then you end each for loop with an end. Remember this is not any programming language that we are writing, so it is just like a pseudo code, you can convert it into a corresponding programming language as per your choice. So this is the forward elimination part. So at the end of the forward elimination we expect that what will be the form of the system of equations? At the end of the forward elimination you have ann xn equal to bn, because all other a's in this row have been made to 0. So next will be backward substitution. So again what we will do, we will see how to formalize the backward substitution and then we will write its corresponding algorithm. So backward substitution. The first one is the most straightforward, so xn is equal to bn by ann. Then what is the equation immediately before that? an minus 1 n minus 1 xn minus 1 plus an minus 1 n xn is equal to bn minus 1. Remember anything to the left of the diagonal has been eliminated to 0. So only starting from the diagonal it is there. So you have xn minus 1 is equal to what? bn minus 1 minus an minus 1 n xn by an minus 1 n minus 1. Let us write the third one xn minus 2. So when we are interested to generalize an algorithm, it is always advisable that you write 2-3 such steps which will give you the idea of the generality, the general parity between each step. That will help you to write it in terms of general indices I, j, etc. instead of 1, 2, 3 like that. So the equation which is before this one, an minus 2 n minus 2 xn minus 2 plus a n minus 2 n minus 1 x n minus 1 plus a n minus 2 n x n is equal to b n minus 2. So, what is x n minus 2, that is b n minus 2 minus a n minus 2 n minus 1 or a n minus 2 n x n that added with a n minus 2 n minus 1 x n minus 1 divided by a n minus 2 n minus 2. In this way, if you want to write x n minus I, x n minus 1 x n minus 2, in this way x n minus I if you want to write, then what is that? B n minus I minus, there is a summation of a n minus I j x j. What is the range of j? So, it is better to write x n minus j. So, a n minus 1 j, you can write this also as n minus j, because you have put the index with x as n minus j. You can clearly see that whatever is the index with x, the corresponding index is with the second index of a. So, here it is n minus 1, this is also n minus 1. So, here this is n minus j, this is also n minus j. So, j will run from first j is 0, because then this is n, then j is 1. In this way, where will it stop? So, I minus 1, because this is 2, it stops with 1, this is I, it will stop with I minus 1. This divided by a n minus I n minus I. So, let us try to write a formal algorithm for backward substitution as we have done for the forward elimination. See, once you get a formula in terms of indices and summation, it is very easy to put that formula in the form of a for loop. So, backward substitution algorithm. So, first is x n is equal to b n by a n n, this is straightforward, this is not within any loop. Then we start with x n minus I calculation. So, I will be starting from 1. So, for I is equal to 1 to what is the last value of x that you calculate? x1. So, that will become 1 when I is n minus 1, because n minus 1 is 1. So, for I is equal to 1 to n minus 1, then to implement this formula you require this summation calculation. So, you can write sum equal to 0 and then you add on with the variable sum to calculate this one. So, sum equal to, we will put the j index after writing the formula, sum is equal to sum plus a n minus I n minus j into x n minus j, where what is j? For j is equal to 0 to I minus 1. Okay. Then that calculation ends. So, you get a new value of the sum, which is this sigma. So, at the end of the calculation of the loop you have the variable sum which is giving this summation. Then you implement the formula. So, x n minus I is equal to b n minus I minus sum divided by a n minus I n minus I, and that ends the for loop over I. Now, once we have generalized this algorithm, the next objective will be to assess the algorithm, that is what will be the number of steps necessary, what is the limiting step, that is out of the forward elimination and backward substitution which one is computationally more expensive, and possibly when something is computationally expensive how to reduce that number of computations. So, these are certain things that we will now try to assess. So, the assessment of number of computations. So, it is very easy to assess the number of computations in terms of the order of computations. So, when we say in terms of order of computations, if we say something of the order of n, for that what we mean is that it is not exactly equal to n, but it scales with n. So, it can be Cn. In that way we will try to assess the order of the number of calculations. So, it is very easy to do that if you look into the algorithm. The algorithm has 3 nested for loops, each of the loops runs up to the order of n, right. This is 1 to n minus 1, do not try to count exactly how many number of times, but it runs up to the order of n because the parameter here itself is n. Similarly, for the loop of I, that also runs up to the order of n, j also runs up to the order of n. So, within this if there is some calculation, that calculation is repeated of the order of n times, that is again repeated for each of these calculations. The loop on I is repeated up to order of n times. So taking this together, these are these calculations are done up to order of n square times, and when you have up to order of n square times calculation, there is an outer loop that itself runs up to order of n. So n number of times, so to say, in order. Therefore the total number of calculations will run up to the order of n cube. So just like as if n for this for loop, n for this for loop, n for this for loop, they are nested. So n into n into n. Remember always that this is not the exact number of calculations, this is just the order of calculations. Number of calculations will require more detailing. So when we say that this runs up to order of n, for each then you have one this r multiplication with this one, this is one calculation, then addition of that, negative of that with aij. So you can break each into some additional parts, two calculations or 3 calculations, but that will not change the order because that does not parameterize with n. So you have to be careful that out of the calculation there are certain calculations which are fixed in number and there are certain calculations which parameterize with n. So whatever is parameterizing with n, that we are including in this order related to n. So the forward elimination will have of the order of n cube, and backward substitution here you have 2 such loops, and but if you see here you have one loop within which this summation is calculated, this I will be scaling with n, and then you have the outer I also scaling with n. So this is of the order of n square. So what is the rate determining step? Forward elimination, because n order of n cube is more than order of n square. So if you say what is the computational complexity of the algorithm, that is of the order of n cube, because of the order of n square will be much less than of the order of n cube. You have to remember that when you are assessing an algorithm, you are considering the value of n beyond the threshold number, so that this comparison becomes important. You are not doing it for n equal to 1. So you are doing it beyond the threshold where n cube is definitely overweighing the effect of n square significantly, so that the net effect is of the order of n cube. So we say that for Gaussian elimination the number of calculations is of the order of n cube, where n is the number of variables and the number of equations that you have. Now when we do this assessment, we learn a moral out of it. What is the moral? The moral is that if you could have the step only as the backward substitution like step, then you could have reduced the order of calculations from n cube to n square. And how that was possible? In the backward substitution you dealt with only triangular matrices, or in this example only upper triangular matrix, but if you are dealing with a lower triangular matrix also it becomes the same thing, only your indices n minus I will be replaced with I, but it is the triangular nature of the matrix that is being handled that reduces your number of calculations here to n square, of the order of n square. So this motivates us to look into possible algorithms where the number of calculations themselves can be of the order of n square, and with that motivation a variant of the Gaussian elimination is designed, which is known as ALU decomposition method. So what is done in this method is a new step that is implemented, that is you factorize A as a product of two matrices. One is a lower triangular matrix, L for lower triangular matrix, and U for upper triangular matrix. So, A11, A12 in this way, A1n, A21, A22 in this way, A2n, AN1, AN2 in this way, ANN is equal to lower triangular matrix L11, then L21, L22, L31, L32, L33 in this way, Ln1, Ln2 in this way, Lnn, these are all zeros. This times an upper triangular matrix. To match the number of unknowns with the number of equations that you get by equating these two, you can normalize the diagonal elements of these two 1. Instead of writing u11, u22, u33, it is possible to normalize those two 1 so that you can determine the others deterministically. So, this is u11, then u12, u13 in this way, u1n, then this is u22, then u23 this way, u2n, in this way the last one is 1 and this is 0 here. So, this factorization what it does is you have to find out what are these Lij's and Uij's given Aij's. The corresponding algorithm is known as Kraut's method. I will not go into the details of this method because it is quite straightforward, but let us just look into one step of the method, and I will advise you to go through the remaining steps of this method by looking into any textbook on numerical analysis. Now, the first step is like this: you have A11 that is equated to what? The first row of this with the first column. So, A11 is L11. So, L11 into 1, the remaining is 0. What is A21? Second row multiplied with the second column. Second row with the first column. So, L21 into 1. So, this row multiplied by this column will give you A21. So, in this way AN1 is equal to Ln1. Actually, you want L11, L21, Ln1 like this, not the other way. So, it is better to write L11 equal to A11 because unknown is L11, L21 is A21, Ln1 is An1. So, in this way you can determine the unknown coefficients one by one. So, once you have found it out, then you can write your system of equation Ax equal to b in the following form: Lux equal to b. So, once you have factorized A into A as L into U, next step you can write U into X, U is a matrix into X, as some z. So, you can write LZ equal to B. So, now you can see this is a triangular matrix. So, Z is L inverse B, where you can use the same algorithm as that of the backward substitution. It is just not backward substitution, it is like forward substitution, because it is a lower triangular matrix instead of the upper triangular matrix, but it is a triangular matrix. So, its calculation is of the order of n square. Then once you know this Z, then LZ equal to B, sorry, so Ux equal to Z, so x equal to U inverse Z. This is like backward substitution, because this is U is the triangular matrix. So, this is of the order of n square. So, it gives you a feeling that this algorithm is of the order of n square and it is better than the Gaussian elimination, but that is elusive. Why that is elusive? Because by assessing the algorithm in this way, you have not taken care of the fact that you require some calculations also for this factorization, and calculation for this factorization comes out to be of the order of n cube. So, it actually does not overweigh this one. When it does not overweigh the number of calculations in terms of order than that of the Gaussian elimination, then what is the utility of this method? So, if you have a method where you have the solution part of the order of n square, but factorization part of the order of n cube, then the resultant algorithm is of the order of n cube, and that becomes same as the Gaussian elimination. So, why at all this method is used when you already have Gaussian elimination? What advantage does it give to us? So, let us stop here today and we will try to answer this question in the next class. Thank you.